Okay, sorry for that interruption. I got an important phone call, and so now I'm going to finish this problem. Let's see, where were we? We identified all the forces acting on the sled, and I like to indicate the direction that the sled is accelerating with an arrow. So the idea here is that the left-hand side represents the sum of all the forces, and the right-hand side represents mass times acceleration, and those two things are equal to each other. Now, when we're operating on a hill, it is often useful to create our coordinate system parallel to the hill. So I'm going to have my coordinate system where the x direction is going downhill and the y direction is perpendicular to the hill. Okay, so now we continue as we do most problems. We're going to add up all the forces in the x direction and set that equal to mass times the x component of the acceleration. We're going to add up all the forces in the y direction and set that equal to mass times acceleration in the y direction. Okay, so because we've set up our coordinate system perpendicular and parallel to the hill, the push force, capital F, the normal force, Fn, and the friction force, Fk, are already set up to be either exactly in the x direction or exactly in the y direction. The one force that's not is gravity. Gravity, we need to split the gravity force into a component that's parallel to the hill and a component that's perpendicular to the hill. So what that would look like is perpendicular to the hill, it pulls into the hill, and parallel to the hill, it pulls down the hill. So this angle here is the same as the angle of the hill. So that means that this side is going to be Fg cosine theta, and at the bottom is going to be Fg sine theta, and the hypotenuse, which is the force itself, is Fg, the force of gravity. All right, so that is going to help us when we make our equations. In the x direction, we have the push force, F, pushing it down the hill. We also have the force of gravity, sine theta, pushing it down the hill. And we have friction pushing it up the hill. So down the hill is positive, up the hill is negative, and those three forces add up to ma because the acceleration points down the hill. In the y direction, we have the normal force pointing away from the hill, and we have Fg cosine theta pointing into the hill, and those two forces are going to add up to 0 because there is no acceleration in the y direction. The acceleration only points in the x direction. All right, when working these problems, it's usually best to start in the y direction, and we can find out that the normal force is equal to the force of gravity times cosine theta, which means that the normal force is equal to mg cosine theta, and then we will use our friction equation right here. So I guess I will, let's see. I'm going to mark this with a 1 just to know that that's where I used force of gravity is mg. And then in my next line, I'm going to use, that means that my friction force is equal to mu sub k times the normal force, which is mg cosine theta, and that is where I used this equation. So I'm going to go ahead and mark that with a 2 so that it's easy for the grader to see where I was using those special case equations. All right, well, now that we know what the friction force is, we can bring that over to the x equation. So this tells me that the applied force, the push F, plus mg sine theta, and I can put a little 1 here too because I used force of gravity as mg again, minus the force of friction, which is mu k mg cosine theta equals ma. Now all that's left to find the acceleration is to divide both sides by mass, and acceleration is equal to the push force plus mg sine theta minus mu k mg cos theta divided by m. Now, don't make the common mistake that people sometimes make of canceling those m's and thinking that that's okay. It's not. You're only allowed to cancel when you can divide the entire numerator by m. So those don't cancel. So we need to make sure that we plug those in. All right. Now I'm ready to plug in my acceleration, and I get my applied force F, which was 51.5 newtons, minus or plus mg sine theta, 88.5 times 9.81 times sine of 18 degrees, minus, minus mu times mg cosine theta, so that's 0.215 times 88.8 times 9.81 times cosine of 18 degrees. And that got me 141.658, but I still need to divide by the acceleration, 88.8, and I get 1.595, or 1.60 meters per second squared. So the sled's acceleration of 1.60 meters per second squared is less than the acceleration of free fall on Earth of 9.81 meters per second squared. And free fall acceleration on Earth is always a good comparison for acceleration, because you're either going to be less than, about equal to, or more than the acceleration of free fall on Earth.